Okay, so maybe I can just briefly discuss with the presenters. So I think that everybody already knows the procedures, so please try to finish your presentation in a given time, also to have some space for discussion. And if it will be required, I will ask you to speed up or slow down. And it is also fine if you will make a short and brief introduction of yourself, as I do not have detailed information about the presenters, and maybe some of the presenters will be different as are listed in the program. Okay?
Yeah.
Good. So we will wait 1 minute and we will start. Fine. I think that we can start because most of you are here. Also, the audience is presented. So welcome to the session 9A, the renewable energy. My name is Michal Frivaldsky. I am from University of Julijana from Slovakia. So welcome everybody. The first paper will be presented by Mr. Dardan Klimenta, and I am giving to him a word, so you can start with sharing of your presentation and your paper proposal.
Okay, thank you for giving the opportunity to present my work, dear Professor Frivaldsky. I will share my screen first of all with you. Do you see my presentation on the group?
Yes, it's okay.
Okay, I will enter now this full screen mode and I will start with my presentation. Today I will present the paper entitled A Novel Procedure for Quick Design of Off-Grid PV Water Pumping Systems for Irrigation. The name of my co-authors are Julijana, Lekic and Dragana, Radosavljevic, and they come from the same university as I, from the Faculty of Technical Sciences, University of Pristina in Kosovska Mitrovica. Other co-authors are from two different universities. Dragan Tasic and Nikola Krstic comes from Faculty of Electronics Engineering, University of Niš, also from Serbia, and Sanela Arsic comes from Technical Faculty in Bor University of Belgrade, also from Serbia. I'm Dardan Klimenta, and I will present this paper now. First of all, this paper contains a lot of formulas, and I will try to present it in a brief way, avoiding equations and too long explanations on them. Because of that, this introducing section is a little bit longer. For example, I listed all the novelties here in introduction, and this is, according to my belief, that the best way to present this paper, which is very rich with details and numerals and equations. For example, this paper proposes a novel procedure that uses the sunshine duration, precipitations, and ambient temperature as inputs. The inputs were collected and taken from the weather online UK service. The effects of different data collection periods and data availabilities are also analyzed and considered in this paper. The proposed procedure also uses as input data sheets from manufacturers for pumping system and PV modules. There are other similar procedures that uses meteorological variables as inputs. For example, one of these softwares are Lorentz compass software. In the paper we listed a number of other softwares which operates in similar way like this procedure. Compass uses the solar irradiation, precipitation, and ambient temperature as inputs, which were collected by the NASA Langley Research Center. For example, this is the first novelty between these two procedures from the compared them, our and this which is embedded in the compass software. For on this slide, for all the novelties from this paper are listed. The second one is the introduction of conditions concerning the dirt losses in the design procedure. The third one is the collection concerning the total number of required modules, the required minimum number of PV modules in one string, and the number of required strings in one PV generator. For example, there are many ways to express these conditions, but comparing our conditions with the existing ones, we found that these can be considered as novelties. The fourth novelty of this procedure is the use of modified Sivkov model that correlates the global normal irradiation with the sunshine duration, elevation angle of the sun, and monthly optimal inclination angle. For example, this novelty can be also considered as the main contribution of our paper. The fifth novelty is the calculation method of the electrical parameters of the PV generator. That means output voltage and output current. The last one, the sixth novelty of this paper, is the use of the monthly mean value of daily global normal irradiance instead of a number of monthly mean values of hourly global normal irradiances, or the peak global normal irradiance. What to say, to add to these novelties is an existing PV pumping system designed using compasses used as a reference for the purposes of comparison and validation. That means like a case study. The results of the comparisons showed a high level of accuracy, and a number of interesting conclusions are drawn from them. The proposed procedure was also successfully validated. On this slide, we can see layout of the water pumping system for irrigation. For example, I will avoid to list all the components of this system, but the main I will list only. I will mention just the main components of this system. For example, this is pumping system labeled with the number 2, PV generator labeled with number 15, and controller PS2 1800 labeled with number 1. And some remarks, for example, this schematic presentation of PV water pumping systems contains some differences compared to the real one which is consistent in this paper. For on this slide you can see two real photos taken during the installation of PV generator and components of this system in the small small village called Zabela nearby the Požarevac in the eastern Serbia. For example, you can see two projections from the front side and back side of a PV generator. And if you read the paper, you can see that the generator has 18 PV modules, but on the roof we can see 20 of them. For example, 2 of them are source of electricity for one small independent off-grid system with batteries running the other devices, chargers, LED lighting, and so on. For example, if we see once again this previous slide, one reservoir tank, water tank is existing on it, but in the practice we do not have it. This is realized with one water pressure of 2 bars, which is equivalent to a height of this water tank. And this is irrigation system, dripping system. For example, on this slide, you can see wiring diagram of the PV generator. Also on the right side of this slide, you can see a manufacturer of PV modules which are connected in this 3 strings, and all together there are 18 PV modules, and they are connected to the controller PC21800. For example, avoiding to explain all the formulas appearing in our paper, I just take this performance charge for the PV water pumping system, just to show to you some details related to the system. For example, in main reference 1, output flow was 5 cubic meters per hour, but in our case it is a little bit higher than it. And also we had in our calculation some differences in pump input power. Manufacturer of this pumping system is the same company, Lawrence, who they are also manufacturers of software compass, which is used for the purpose of comparisons in this paper. On this slide, we can see Sivkov model. Really, this Sivkov model can be found in the literature under the name also like Sivkov empirical correlation or just Sivkov correlation. And this correlation was originally developed for the latitudes between 35 degrees and 65 degrees north. And I take just 2 formulas from our paper and presented original Sivkov model and modified Sivkov model. This the second equation is our contribution and one of novelties presented in this paper. For instance, with this slide, I will start to present our results, obtained results of this study. For example, this table represents a comparative presentation of the results obtained by applying compass and our proposed model. For example, columns labeled with compass relates to the Lorentz compass software, and columns labeled with double P, they contains results obtained by us. And comparing all of these numerals, we can see that the differences are minor and negligible between two models. Some differences, of course, exist, but I will remember them in the concluding section. This slide shows the first chart shows the monthly mean values of daily ambient air temperature. The values colored with black with dots are from the NASA Langley Research Center, by the second one comes from the Weather Online UK service. And these are inputs not calculated by us. Also in the second chart shown on this slide are also inputs taken from the services. Bars labeled with A are also from the NASA Langley Research Center, while the second one are from the Weather Online UK service. This second chart presents monthly mean values of daily precipitation in millimeters per day.
Dear Dardan, I think we should go to the conclusion because...
Yeah, I'm near. This is last one. I was so quick. These two charts shows our results of our calculations. The first one shows the monthly and seasonal mean values of daily global normal irradiation on a south-oriented surface inclined at 25 degrees in kilowatt hours per square meter and per day. On the second one, we can see the monthly and seasonal mean values of daily electricity generation from PV generators. Both are presented together with the results calculated by compass, and reader can see differences between our and the existing ones, differences between results. And the last one chart, the diagram shows the monthly and seasonal mean values of daily water production. Differences also exist between them, and I will remember them in the concluding sections. The first one, conclusion, I remembered it in introducing section, and I will avoid it now. The most important conclusion is the second one here. The application of the Sivkov empirical model resulted in overestimations of available solar energy in average by about 20 degrees, and electricity generation in average by about 5.5% at the considered site. But there was no need to redesign the PV generator. Compass gave solution with 18 PV modules. Also, we get the same one with 18 PV modules of the same type. The daily water production for the month of May, having the lowest global normal irradiation value in the irrigation season, is by the 13.75% higher than daily required amount of water. This confirmed that the proposed procedure is in line with the relevant standards. Both the proposed procedure and software Lorentz compass gave the final design solution consisting of the same components. It is shown that parameters such as the data collection period and data availability can affect the values of meteorological variables used in the design procedure of the off-grid PV water pumping systems. Accordingly, it's recommended that the data collection period should be equal to or longer than 20 years, and that the data availability should not be less than 70%. I didn't have time to, to discuss this issue. This is just said as in this mentioned in this conclusion, and it will be left to the readers to see our old paper, which is published in our journal. Also, it is found that there are no significant differences between the values of meteorological variables, which can be. It is also found that the presented worth of the costs for the considered PV pumping systems is $19,760 US, excluding costs for the diesel-powered electric generation and piping. Thank you for your attention, and sorry for over timing.
Yes, thank you very much, Dardan. So yes, the paper is a little bit long, so it was also necessary to present all the results, and it is seen that they are also practically verified. So very good. Maybe one question from the audience, if there is some question. Okay, so maybe later, so you can write it in the chat, and then you can have also a discussion after the session. So thank you once more. And now,
dear Professor Frivaldsky.
Yes, now we can continue to the second contribution within this section. So I would like to welcome Mr. Pavel Šimon from University of Julijana. So he's a colleague of mine. He's acting as an assistant professor. And now I would like to ask once more, Dardan, you should end sharing the screen.
Yeah, I'm trying, but
it's not working. Yes, now it is good.
I'm closed. Okay, it's okay now?
Yes, it's good. And now I would like to ask Mr. Šimon to start sharing so we can see the presentation. So please, you can make the presentation of your paper.
Thank you. I would like to present papers of technical potential of built-up area in the Slovak Republic to produce electricity from solar radiation. I am from Julijana University as our chairman, from same faculty, but from different department. And we are working, two of us, me and my colleague Michaela Hola. Introduction, I will divide it in this parts of my presentation, and this research wasn't supported by any grants, only by my earnings in faculty. That thank you faculty for supporting this research. Purpose of this research was our commitment to our children to leave them beautiful earth more harmed than before. Of course, EU and our country commitment, and I need to say that renewable energy sources are quite different from traditional energy sources. It could be distributed everywhere, but could be really volatile, could be close to consumption, and they have a huge variation of generator size, from one panel to many megawatts. And sun deliver a base portion of energy, but we still cannot use it very efficiently. But how many this energy can we use? That is purpose of this research. At first, I need to say there is plenty of tools to evaluate any individual place of PV production. One of the best is PV GIS from GRC of European Commission. It's free tools on web, and you can evaluate any point in Europe, part of Africa, and part of Asia. Next, very good tools for point evaluation is PV Planner from Slovak commercial company SolarGIS, and they have more than 50 years of meteorological data and satellite data with 15 minutes granularity. But all these tools are useful for evaluation of exact PV installation site, but is not useful for evaluation of huge area as is Slovakia. But from these tools, we can say that PV production in Slovakia varies in ideal condition from 900 to 1,250 kilowatt per installed kilowatt peak. Next thing is what we need cover with renewable energy. Slovakia is one of the largest country which has largest portion of low energy, low emission sources, because more than half of our consumption comes from nuclear energy. Next, 11% is from hydro, which some of them are considered as renewable, but above 10 megawatts is not considered as renewable, but still is really low emission sources. Then we in our population, we need cover mainly these thermal conventional sources of electricity. And Slovakia has consumption roughly about 31 terawatt hour per year of electricity. We used official data from statistical office of the Slovak Republic, where they cover in chapter 4.1 agricultural, forestry and fisheries, their point of view for non-agricultural land, which there is called built-up area in square meters. And this data we collect in the table. There is only 10 districts shown. We have 79 districts in Slovakia, but we see that the highest portion of built-up area is Bratislava, which is more than 58% of the land is covered with some concrete, asphalt, or some artificial structures. The lowest district is Brezno, which has only 2.13% of built-up area, but generally in Slovakia is almost 5% area with some artificial structure, which is 2.3 million square meter from 49 million of square meter. There is visualization of percentage of built-up area. You see that only our capital Bratislava and the second highest, biggest city in Slovakia has different colors, and all the data we combined in a methodology how to make calculation of possibility of producing PV electricity. There are some conditions which we use. They're described in this text and more detail in our article. We use 15 PV lifespan of minimum. We didn't calculate any degradation of PV system. And next, we use general panels with 333 watt power and with surface 1.65 times 1 meter. And because our variation of PV production is from 900 to 1,250. For this calculation, we used constant value as 100 kilowatt hour produced by 1 kilowatt of installed power. Then we made a calculation which is in this equation, and this result with constant that any square meter of inbuilt area can produce 202 watt hour of PV energy. This we combine in calculation, and it result with which what can be installed in any of district. As you see, even Bratislava is most covered by concrete, but still their production possibility is quite low because it's quite low, small district. But Prešov can produce about 10 gigawatt of installed power, which result in 10 terawatt hour annual production. In total, Slovakia could theoretically produce 482 terawatt hour per year from PV if all that land will be covered by PV, which of course is not possible in reality. There is a map of any district in Slovakia, how many these districts can produce. You can see that those south part of Slovakia, they have a nice sun covering and even a good portion of built-up area. This means all of them can produce above 13 terawatt hour of PV energy. I came to conclusion. Hypothetical production of built-up area is 482.3 terawatt hour, and some district can produce half of Slovakia electricity consumption. Of course, it's theoretical, but still is 15 times more than our consumption. It is hypothetical because it not consider places where we cannot install PV. There are no rowing and orientation considered, and grid connection is not considered with this theoretical approach. Of course, need to be improved, and there is continuing of our work. We are now trying to introduce map recognition. As you can see, map of Google can list all the buildings, which will give us much reliable number of production. We need to introduce more quality data source, which we will elaborate each district with their average solar production, and we need to combine with other methodology. Now we are working with calculation of EV consumption, charging possibilities when we will replace all our cars with electric cars, and we have more than 3 million cars in Slovakia, and sometimes in the future, I don't know, 5, 10, 15 years, all that internal combustion engines will be replaced with electrical, and all the cars need to be charged. Then now we are working how to combine this possibility of charging with PV production, because we see that charging of PV is quite difficult with our current sources. Thank you for attention. If you will have any question in future, you have my contact.
Okay, so thank you. So you avoid any discussion right now? No.
I say that
yes, in future, yes. Okay. So thank you for presentation. The study is very interesting, and I think there are a lot of issues which can be addressed and researched in the future for successful implementation of this study. So maybe now we can open a discussion from the audience. Are there any questions? So if there are no questions, you can see a contact on my colleague, so you can directly write him an email with some questions, and I think he can provide the information related to this study and how to proceed for maybe other countries. Good.
Okay, thank you for the opportunity to present.
Thank you. So please stop the sharing of the screen. Okay. And now we are going to a third contribution. It is from the University of the Sofia, Bulgaria. The presenter here is Mariya Aleksandrova. And the topic of the paper is already shown on the screen. So Mariya, it's your time. You can start your presentation.
Thank you very much, dear participants. My name is Mariya Aleksandrova, as you already understood. I'm coming from the Department of Microelectronics. This is Technical University of Sofia, Bulgaria. And I will try to present our work related to implementation of a system for utilization of thermal energy in compact solar energy harvester. This is the outline of my presentation, starting with a few introducing words about the motivation and the aim of the work, some details about the energy harvesting module fabrication, principle of operation and design of the electronics circuit for micropower processing, printed circuit board fabrication, components mounting, and system testing. Actually, our contribution is in the technology part, and I'm directly involved in the fabrication of the energy harvesting module. But I will do my best to give you sufficient detail about the electronic circuit as well to capture the idea of the entire module. So what's the primary idea here? The continuous irradiation of any solar cell causes rising the temperature in the films, and this results in decreasing the efficiency of energy conversion. So this is especially strong expressed if the modules are thin film and compact, small size. So in order to cool such a kind of system, you will need some kind of element like Peltier element, like thermoelectric generator, but it would be good if it is somehow integrated together with the solar converter. Well, if this thermoelectric generator work in the Peltier mode, it could take some energy from the heat, could convert this energy into temperature difference and cool back the solar module. If this is organized like a thin film, like a micro device, it could be split into a variety of segments. One of them could be responsible to absorb the heat and generate the voltage. It could be supporting additionally energy to the battery or storage capacitor, and the rest of the energy could be returned back as a second part of the module that could work at the opposite mode and use this energy to generate temperature difference. I mean, to cool the overheated module and maintain constant temperature. Normally, such kind of system exists, but they use such kind of bulk thermoelectric converters, which normally requires great temperature difference across the PN junctions. And to achieve this, it is necessary to use heat sink at one of the sides, opposite sides to the across to the object being cooled. And this makes the system larger size, lack of compactness. So for practical applicability of a smaller system, we need to make it more compact. So regarding the power conditioning electrical circuit, it must be inserted somehow between the energy harvester and the electrical load that consumes this energy, because it is necessary to establish the signal to appropriate level, especially if it is fluctuating or lack of periodicity. So there are several approaches that have been discussed in the literature, but the most popular actually is the Dixon charge pump. It is some kind of amplifying DC-DC converter, boosting converter with a charging pump. And it was reported that if you have an input 1 voltage, you can convert it into, gain it into almost 16 volts. So it is very favorable for such kind of low voltage input that is expected to come from this system, because the temperature difference is actually less than 20 centigrades. A few words about the energy harvesting module fabrication. This is the solar converter part, and here this is the details about the thermoelectric converting part. So actually we use lead-free perovskite materials for absorbing layers in combination with cadmium telluride quantum dots. Both of them are responsible to cover the entire wavelength range of the spectrum, and some supplementary layers, titanium dioxide, gallium doped zinc oxide. They are serving as supporting the charge carrier transportation. Radio frequency vacuum deposition sputtering is used for the oxide coatings, and spin coating for the rest of the films. Regarding the thermoelectric converter, we used MEMS technology for three-dimensional high aspect ratio objects. It means thick film for photolithographic patterning and electroplating for growing the thermal legs into these thick films in shape at the thermal legs. So we use this approach because the diameter of each thermal leg is smaller than the height, and it is like a high aspect ratio object. They could be connecting an array according to a standard planar photolithographic process. So regarding the electronic circuit for micropower processing system, we used integrated circuit LTC 3107 linear technology manufacturer. The details that are given are that it consists of DC-DC boost converter, working with ultra low input voltage, controlling the power to extend the battery life. It could be also used in combination with some supercapacitor to store excess of the collected energy when it is available. And it could use the voltage at one of the pin related to the battery, this one, not only as a power source for the output when the input energy is absent, but also as a reference voltage to regulate the voltage of the output and to track the battery voltage like a feedback. So there are some external components that must be mounted to the integrated circuit. They have to be calculated properly. When there is no energy available for storage capacitor, this output capacitor should be sized to provide the necessary current when the load is switched on. And in the second case, we can have additional storing capacitor that could be charged up to 4.5 voltage. And there are some additional consideration in the design related to the transformator. You can use specific ratio, turn ratio of the transformer. If it is 1 to 100, you can set the startup voltage or so-called startup to 20 millivolts, not microvolts, millivolts. It means that the whole system could work if the input is applied 20 millivolts. It happens when the temperature difference across the thermoelectric converter is less than 10 degrees Celsius. Here is the step-by-step PCB fabrication of the system. Actually, it is conventional flow of the technology, nothing special here. Maybe I have to mention the different etching solution for patterning the copper wires of the PCB. It is not ferric chloride, which is standard conventional etcher. Because it's strongly isotropic and strong undercut effect could appear and could completely remove from the PCB this critical spot, the place where the specialized integrated circuit is mounted. Actually, the distance between each pin is 12 micrometers, and the width of the contact path is 200 micrometers. So this undercut would completely remove these paths there. So we replace it with a non-isotropic etching solution from sodium persulfide. And the success in the system running depends on the positioning of this microchip. It is hard to mount it because it is inverted flip chip package. At the back side of the package there is a cooling contact pad for heat dissipation, like a sink, like a layered sink, and we must keep to avoid short circuit by a side positioning. So we use special kind of die bonder and component placer with precision greater than 5 micrometers. This dispensing needle put solder paste on the contact pads. Here you can see a microscopic views, and this machine has the function to precisely set and program the thermal profile of soldering process to avoid boiling of the solder paste and void formation. So this will guarantee reliable electrical and mechanical bonding. And here the plots are just to demonstrate that even at temperature difference less than 10 centigrade Celsius. The cold startup voltage exceeds the threshold for the system, so fluently the charge could flow to the storage capacitor and the battery. This is just to demonstrate the capability for the working ability of this double solar plus thermal converter. As a conclusion, I can summarize that the proposed system is simple, compact, can meet the needs of low power consuming device, could be used as additional backup source of the solar energy harvester, could use part of this energy not for battery charging, but to charge the Peltier module to cool the solar elements, preventing efficiency drop due to overheating. And something that could be added, I'm realizing now that I didn't mention anything about the practical applicability, I mean, where we need such kind of system. It is suitable to be implemented in informational displays on the bus stations, which are independently supplied from solar. That could give us information about the bus number when it's arrive and depart and so on, and for the street lights. Thank you very much for your attention.
Thank you for your presentation and this practical approach, because I had one question, but you already answered it, so it was directly related to the practical implementation. But maybe I would also ask or propose to give some information related to the dimensions, because you have been speaking that the system is very small related to the microchip or the integrated circuits. So it would be nice to know what are the dimensions of the final system, and also some information related to the efficiency of the conversion.
Okay, about the size of the whole system, the module is in size 8 centimeter in width and 5 centimeter in the other dimension. It is means the PCB. Directly on the PCB, it could be mounted the solar module, which is 2.5 centimeter to 2.5. It is square size.
Mm-hmm.
The conversion efficiency of the solar module in general is 25%.
Mm-hmm.
It cannot be expected more because it is thin film, not polycrystalline or monocrystalline silicon. It is lead-free perovskites, which are relatively new materials and still under investigation.
Okay.
So in general, this is...
Okay. Yes, so in general, the dimensions have been adapted to the solar system, or the, yeah.
Yes, the dimensions are 8 per...
So this is a one cell, yes, or... So
this is for the PCB together with the mounted solar module on the top of the PCB, and together with the integrated thermoelectric cooling module directly under the solar cell.
Okay. Some other questions from the audience?
I have one question also.
Okay.
Dear Professor Frivaldsky, you asked about efficiency for PV module, but my question is about efficiency of thermoelectric module.
This was also my question. So the conversion efficiency from the thermal to electric.
Yeah, but
yes, it is approximately the same, but actually we need more investigation related to the long-term stability, because we have no such data to summarize about the efficiency. So it is not really trustable to see this momentum efficiency. But it is close to 20%.
20%. But colleague Aleksandrova, you said that 25% is efficiency of PV module. And during your presentation, you said that the difference, the temperature difference between contacts of a thermoelectric module is just 10 kelvins, 10 degrees Celsius.
Could be. This is the minimum.
Just one moment, please. If you have such a difference between contacts of thermoelectric modules, its efficiency is lower than 1%. But I cannot say exactly how is high, but is lower than 1%. Is it possible to use thermoelectric generator as cooler for PV cells?
Yes, if it is integrated in the same system of fabrication of the thermoelectric module, because it is split into two parts. One half of this part is responsible to absorb the heat and convert into electricity. And the second part, fabricated by the same technology, use part of this energy to work in the reverse mode. If, of course, if you assemble with commercially available components, the situation will be not the same. Yes, it depends on the thermal capacity and the materials involved, but in this case, could be possible.
According to my opinion, it seems that you cool the PV cell just by mass of the thermoelectric module, not with the harvesting heat by it, because efficiency is too low for difference of 10 kelvins.
Well, it depends on the ambient temperature as well.
Take this remark for future research. This is a really serious lack of that, according to my opinion.
Okay. Okay, so maybe this is a good recommendation for the future.
Thank you very much for your opinion. We will think about this. Thank you very much.
Yes. Welcome. Okay, so thank for this contribution. And now we are going to a next contribution, which is from the Lekic University. The presenter is Ahmed Emre Onay, and you can see already the topic of the contribution. So, dear Ahmed, I'm giving you a word, and you can start your presentation.
Thank you, Professor. And as you can see, my name is Ahmed Emre Onay. First, let me introduce myself. I'm a master's student in Lekic University in Turkey, and together with my supervisors, Dr. Emrah Dokur and Professor Mehmet Kurban, we worked on performance comparison of new generation parameter estimation methods for variable distribution to compute wind energy density. So what we mainly focus on, I will first introduce you with the presentation outline. I'll start with the introduction, and I'll talk about the materials and methods we've used in our study. And then I'll talk about the results, and I'll end with the conclusion parts. And so, as you all know, the renewable resources are increasing, our use of them are increasing, and what we mainly focused on in our study is wind energy. And in order to install wind energy in some specific location, you first need to identify the wind speed characteristic of that specific site. So there are some certain tools used to do this job, and what we have mainly focused on in our study is the variable distribution, the two-parameter variable distribution. But there are many other tools like Burr, Rayleigh, and some neural networks, and these also can be helpful. So for this variable distribution, there are some certain parameter estimation methods, and in our study we have compared these parameter estimation methods, and the data we have used is actually from the 32 cities in the 3 regions of Turkey. So as you can see here, all these we have taken the wind speed data from all these cities, and we have used them to compare the parameter estimation methods. And the wind speed data is consisted of 3 years of hourly wind speed data, and it's 50 meter heights. It's converted from 10 meters, and I'll talk more about this in the next slides. So as you can see, in some regions the wind speed is kind of low, and in the others, the 2 regions, the wind speed, wind energy density is higher. These 2 regions, Marmara and Aegean region, and the main reason is that they are closer to the coastal areas, and it's actually the places you can see the wind energy is utilized. So for the materials, we have used MATLAB software to make a comparison between these parameter estimation methods, and we have taken the graphs and resolutions out of MATLAB software. And when we talk about the power law, as I mentioned before, the wind speed data was of 10 meters, and in the literature there are many tools to convert these data, and we have used power law to convert it from 10 meters to 50 meters, so it could be more workable. And the comparisons we made is consisted of 3 steps. The first one being the efficiencies of these parameter estimation methods in estimating wind speed probability. And the second comparison we made is the wind energy densities that were calculated by these methods. And the third one is we have compared the performance criteria of these parameter estimation methods, and these are root mean square error, wind energy error, and coefficient of determination. And some of them are used in statistics as well. So the reason we use 2-parameter variable distribution is that, as you can see, the raw data is the graph, the first graph, and the 2-parameter variable distribution takes this data and makes it in a more workable way. And by taking this graph, we can actually make a better comparison. So when we talk about the 2-parameter variable distribution, I'll briefly just talk about this. It has 2 parameters, shape and scale parameter, and it's got 2 functions, probability density function and cumulative distribution function. These 2 functions involve the shape and scale parameters, and these parameters are estimated by these parameter estimation methods that I've talked about. And in our study, we have used 6 of these parameter estimation methods, and 3 of them are well-known parameter estimation methods, and 3 of them are actually newly proposed. So graphical method, maximum likelihood method, and justice moment method are mainly used in literature to make comparisons. And for example, wind energy intensification method has been proposed in the last year, in 2020. So we have taken all these methods, all these 6 methods, and compared them in 3 steps. And I'll also talk about these parameter estimation methods briefly. They mainly calculate the shape and scale parameter in their own way. And we take these shape and scale parameters and place them in variable distribution to make a better comparison. So In the second step, I talked about the comparison of wind energy density, and as you can see on the right, the actual wind energy density is calculated with this formula, and the variable wind energy density is calculated by the incorporation of shape and the scale values. And so we can compare the parameter estimation method's performance as calculating the wind energy density. And so the third one is the performance evaluation, and these are the evaluation methods we have used: wind energy error, root mean square error, and coefficient of determination. So two of them are actually mainly used in statistics as well. So when we talk about the results, the graphs on the top show the probability distributions for each region. So the blue bar shows the actual wind speed data, and the line graphs show the estimations of these parameter estimation methods. And we want them to be as close to the actual values as possible. So when it exceeds a certain number of parameter estimation methods, they may overlap. So for this reason, we have actually taken, in the second graphs, you can see that the closeness of these values to the actual values. So we have highlighted the closest ones to the actual wind speed values. So the closest ones are the better performing ones. And for the Aegean region, the power density method is the better performing one among all the 6. For the Central Anatolia region, again, power density method is the better performing one overall. And for the Marmara region, power density method is the better performing one. And for the second step, we have compared these parameter estimation methods performance as calculating the actual wind energy density. And this is the actual wind energy density on the left for each region. And when we take a look at all these calculations, what we can see here is that the power density method is actually has actually made the spot on estimations for each region. So it is the better performing method for the 3 regions. And the close to following ones for each region, we can say that energy pattern factor methods and wind energy intensification methods. And for the third comparison we made, it's performance criteria, and for the performance criteria we've used for wind energy error, we are looking for the values closer to 0, and it's the same with the root mean square error. And for the coefficient of determination, we are looking for higher values, and it's more closer to 0, say closer to 1. So these are the results we have gotten from these performance criteria for each region. This is on our paper as well. You can check it out. We have highlighted the desirable values for each city. So for each table, I can say that it's for 3 regions. So for the resolutions, I can say that for wind energy error criteria, power density method is the better performing one. But for the root mean square error and for coefficient of determination, Justus moment method is the better performing one. And when we take an overall resolution of these all regions, we made a ranking here. Justus moment method for the values, for the desirable values, is the best method in the third comparison, and then follows maximum likelihood method and energy pattern factor method and power density method and so on. So overall lowest error values have been achieved by just this moment method here. And when I talk about the conclusions, I can say that for the first comparison, probability distributions indicate that the power density method is the most accurate one. For the second comparison we made, it was about the wind energy density estimation. The power density method was the best performing methods among all. And for the last comparison, just this moment method has achieved the lowest error values, but power density method has had acceptable error values as well. And overall resolution shows that the power density method is the better performing method among all. And thank you for listening, and thank you for your attention.
Dear Ahmed, thank you for your presentation. Now I am opening discussion. Are there any questions? So maybe just because of my interest, so these methods have been, let's say, well known. There is no method that you researched or delivered by yourself.
No, it's not a new method by me, but there have been a couple of new methods that has been proposed. Especially, I talked about the wind energy intensification methods, and this has been proposed recently. And energy pattern factor methods and power density methods they are kind of recent as well. But it's not there is a method proposed by me.
Yes, maybe in the near future.
In the future, yeah. I am hoping in my doctorate work I am hoping to propose a new method.
Yeah.
Thank
you. Some other questions? Good. So thank you for your presentation once more. And now we continue to the last contribution. It is the paper from the Technical University of Ostrava, so our colleagues from the Czech Republic. And I would like to welcome Mrs. Tereza Paterova, who is a presenter of this contribution. You can see already the presentation and the title of the contribution. So dear Tereza, it's your time. You can start with the presentation.
Okay, thank you. Good afternoon. My name is Tereza Paterova and I'm a research worker and also a PhD student at Technical University of Ostrava. And I would like to introduce you to the content of the paper that I wrote in collaboration with my supervisor, Michal. The article is focused on predicting daily solar energy for the next day, and the prediction is based on pressure values. The approach used for forecasting was a deep learning approach in combination with multi-layer neural network. So predicting future solar irradiance is an important topic in the renewable energy field to improve the performance and stability of the system. For example, this parameter is used to improve the planning and operation of photovoltaic system. So the forecast could be used as a support parameter to control the operation duty cycle, data collection, or in communication activities at energy independent and also energy harvesting embedded devices. The solar availability can be predicting using many methods, such as statistical methods, some artificial neural networks, or support vector regression. We chose a deep neural network because it add a complexity to a model without specifying what form the variation should take and allow the extraction of high-level features. So we were focused on the application of deep learning and neural network approaches, especially on deep feed-forward networks. There were used a back propagation method to train the network in combination with deep learning methods such as optimization, gradient descent algorithms, batch normalization, and so on. I'm sorry. Now something about the experiment design. Here is on the figure shown the deep learning experiment algorithm for one configuration. For neural network training and testing were used two data sets, which was hourly measured pressure values are marked 2012, 2013. As you can see, first test configuration of deep learning method was set. That means there were chosen settings of optimization methods, gradient descent algorithms, etc. Then the neural network training was performed using the dataset 2012. And then the trained network was tested using the dataset 2013, which results were the predictions of available solar energy for the following day. Then the evaluation parameters of the resulting dataset were calculated. These parameters were used for comparison to other test configurations of deep learning methods, which were performed. And this cycle was repeated for all experimentally selected combinations of settings. And then the results of each combination were compared to previous published approaches, and an overall evaluation was provided. Now, about the results. On this slide, you can see a table with the results of the best combinations of settings. For example, the results show that the N2 configuration has the lowest value of MAPE of all proposed settings combinations. It was also shown that the comparison of MAPE values of the N1 and N2 configurations, which had the same settings except for the number of layers. So it is better to choose a larger number of layers for a more accurate forecast. A1 and A2 configurations also had the same configuration apart from initialization method, and their comparison showed that the mode with sigmoid is better than with Xavier, for example. On this slide, you can see a table with 3 best experiment configurations and a graph of their prediction during the year against the target. The differences among these individual configurations are not statistically significant, as evidenced by the MAPE values. The graph shows that the neural network presents satisfying predictions in early spring, autumn, and winter, because there were no significant fluctuations in daily solar energy availability. In terms of summer months and late spring, the forecast did not correspond to sudden fluctuations, which are typical for these months. the comparison of the results to the reference approaches. The table on this slide shows the difference between the best result of our experiment, which has N2 label, and the reference approaches. The comparison of maple values shows that the best result was achieved using the support regression trees, the abbreviation as TR. It's here. SRT, I'm sorry, which exceeds our predictions obtained. However, the best forecast from our trained neural network surpassed all the above support vector regression models. The abbreviation is SV, so that's here and here. Or had comparable results with other approaches such as artificial neural networks A and N, general regression trees, it's here, and others, as you can see, based on the MAP value. So the summary of used deep learning approach for solar energy forecasting is that it was satisfying predictions. There was satisfying predictions in early spring, autumn, and winter. But on the other times, it did not correspond to sudden fluctuations. Also, I'd like to mention that the time and computational complexity for neural network training was considerable, and therefore it was assumed the network was trained on an external computer or a cloud, where only the network parameters have been obtained and transferred to the embedded device. Using the parameters obtained in this way, it was simple to implement a prediction model of a neural network on an embedded system, because in the prediction phase, the network is represented by a lookup table. It is important to emphasize that the outcome of the learning process was greatly affected by the initialization of the parameters that used pseudo-random numbers generators. Therefore, different neural network training results could be achieved with the same settings. A possible improvement could be the use of more datasets measured over several years to train the neural network. And also another possible aspect could be using the dropout or L2 control method.
Okay, thank you.
So thank you so much for your attention. And if you have some questions, please let me know, or my colleague, Michal Pravosek.
Okay, unfortunately, chair should leave us a bit early before the session ends, and I will take care of you.
Okay.
Okay, and do we have any question from auditorium?
Just one from my side.
Okay, please, Dardan.
Thank you, dear Darius. For example, it is very clear what you did and what your research was. But for me, there is one unknown thing: harvestable solar energy from atmospheric pressure.
Mm-hmm.
Could you please give some details related to that? Is it possible in practice to collect energy from the sun, from
Yes,
the atmospheric pressure? How the name of the device or sensor somewhat?
It's not collected from the pressure. It's just based on the pressure. We know how much energy we are able to collect.
Mm-hmm. Okay, thank you.
You're welcome.
Okay, do we have any more questions? I have maybe two questions. How did you decide which method can be used in your research, and how did you choose which ones?
We choose deep neural networks, and it was random. It wasn't any big reason to, because my supervisor Michal already did this topic with different approaches, and now he chose the third one.
So maybe they were chosen not accidentally, but it is based on some parameters. Because if you are going to evaluate, let's say from the scratch, all methods, so why? Because you can go just over the references, analyze what other authors did, and do not waste time in this area. So maybe you can, let's say what kind of parameters you evaluated, and based on these parameters, you probably chosen some methods. So are there any parameters, any critical parameters in order to choose proper neural methods?
I don't know what to say.
Okay, I see. Okay, there is also in your paper that you analyzed some references, and there are a lot of methods which were analyzed in one reference. And so question would be like this one: maybe it was not worth to analyze such amount of methods if somebody already analyzed and made some conclusions that maybe there are only 3 the best method, and the rest of them do not fit in your research scope. So how do you think, have you paid attention to that fact, or just
you're
took
right.
everything what exists and made analysis?
Yes, that's right. It's a good idea to do that in this way.
Okay. If we do not have any more questions, so we can end the session and today, the conference of today. And I hope to see you tomorrow at 9 o'clock in local our time, European East time. Okay.
Thank you.
So
Okay.
see you.
Thank you.
Bye.
Bye.
Bye.